Okay, so we are going to look at one more example of solving a system of linear DEs using this elimination technique. Where this one differs from the previous example, in one way you can see it's already written in operator notation for us, which is nice. We can skip that first step. We also have a second order equation, whereas in the first example we were only dealing with first order equations. And not only that, in our previous example we didn't see any functions of t showing up. Whereas in this case we do have a t here. So what's going to happen is we're going to end up doing all the same techniques, but we're going to look at solving a non-homogeneous equation in the process, which means we just need to use undetermined coefficients or variation of parameters or one of those techniques. But it otherwise is going to look essentially the same. So doing elimination, let's take a look at what we might want to eliminate first. It looks like both of these guys have a d plus 3 involved. Let me multiply, or not multiply, but operate on my top equation by that d plus 3 that I'm seeing there. So that's going to look like d squared d plus 3x minus d plus 3y equals. Now, this is d plus 3 operating on t. Okay, and think about what that does. D plus 3 operating on t. So I take the derivative of t, which is 1, and I also multiply t by 3, which is 3t. So 1 plus 3t, or 3t plus 1. Okay, on this left-hand side, I operate, what is it that I want to do? It looks like it might be pretty easy to eliminate the y first. So this term compared to this term is missing that d right there. I'm going to operate on both sides by d. So that's going to give me d plus 3x plus d plus 3y equals. And then since I'm operating with just a derivative, d, the derivative of 2 is just 0. Okay? So now we can add these two things. We're going to get cancellation here. And remember, at this stage, these don't match, so they're not going to cancel each other out. But we do want to distribute things in and solve as we would otherwise. So this is going to give me a d cubed here. I'm going to get a 3d squared and another d squared from there, so that's plus 4d squared. And then I'm going to get a 3d right there, so plus 3d. X equals 3t plus 1. Okay? Now, I solved this thing using one of the techniques that we talked about for non-homogeneous equations. I would like to use undetermined coefficients, the superposition approach, I think. Actually, I think I'm going to use annihilator approach. So either way, I need to find my complementary solution first. So I'm going to take my operators here, use it to find an auxiliary equation. Okay, that's m cubed plus 4m squared plus 3m equals 0. This guy factors pretty nicely. M times m plus 1 times m plus 3. And that's equal to 0, which means m is equal to 0, negative 1, or negative 3. That means I have a complementary solution of c1 plus c2 e to the negative t plus c3 e to the negative 3t. Okay? Next up, I want to use the annihilator approach. So the annihilator approach is going to have me, since this is a linear polynomial, I want to operate on both sides with a d squared. Okay, so if I were to do that, d squared times d cubed plus 4d squared plus 3d x is equal to, that d squared is going to zero that out. Okay, and this leads me to the auxiliary equation. Notice the only difference is that I'm taking this thing and multiplying it by another m squared there. So I get m cubed, m plus 1, m plus 3 equals 0. And that leads to the following. So I have a 0 with a multiplicity of 3 here, giving me c1 plus c2t plus c3t squared plus c4 e to the negative t plus c5 e to the negative 3t. Okay? Remember, the way the annihilator approach works is you compare this to your complementary solution, and you look for the terms that are missing, basically. So I have a constant, I have an e to the negative t, and an e to the negative 3t all showing up in there. I do not have those guys. So that's going to determine my particular solution. Yp is going to be of the form at squared plus bt. Okay? Now, my differential equation that we're going to be using this on is up here. That's a third order equation, which means I need up to my third derivative, which, because it's a polynomial, is our favorite case of evaluating that. So this becomes 2at plus b, y double prime is equal to 2a, and yp triple prime is just equal to 0. Okay? Plugging that in to, I should stop for a second. So I'm forgetting which function I'm talking about. I've been using y so much because we're used to doing that I forgot that the function is actually x, not y. So fortunately my y's look a lot like x's. I should be able to fix that pretty easily. That's actually an x there, and then all of these are xp's, not yp's. Okay. Hopefully that helps avoid some confusion. Okay, here's my dE up here. Third derivative is 0, which we found down here. 4 times my second derivative, that's 4 times this. 4 times 2a, plus 3 times my first derivative, plus 3 times 2at plus b, should equal 3t plus 1. Or 6at plus 8a from this guy plus 3b should equal 3t plus 1. Equate coefficients, right? So this means 6a is equal to 3, which means a equals 1/2. Substitute that in for the a here. I get 4 plus 3b, and that should equal 1. Solving for b, that'll give me b equals -1. Okay? So my particular solution is given by these coefficients right here. So now I know that x of t is going to look like I have x of t right here. So I'm gonna take my complementary solution, write that first. C1 plus c2 e to the negative t plus c3 e to the negative 3t. Use my coefficients on my particular solution now, plus 1/2 t squared minus 1t, or minus t. Okay, now I want to solve for y, and it's going to follow similar steps. Okay, so looking at y now, up here, let's use this form right here. Or no, I'm sorry, let's use this one. I want to eliminate my x terms. Notice I would still need to operate on this top equation using a d plus 3. And then this x will be missing that d squared, so I'm going to use a d squared on my second equation. All right, what's that going to look like? Well, I'm going to have d squared d plus 3x minus, this will look like d cubed y equals, d squared on t up here, this guy. Second derivative of t would just be 0. So that's going to become 0, right? And then, let's see, what else do we have? On this part down here, I need to use a d squared. Oh, shoot, no, I'm writing the wrong thing. Let me fix that. I forgot which equation I was dealing with. D squared d plus 3x minus d plus 3y equals d plus 3 operating on t. We did that already. That was equal to 3t plus 1. Okay, I messed that up. Second equation, I need to operate on both sides by a d squared. So that's going to look like d squared. In fact, since we're trying to eliminate the x, let's make it a negative d squared so that when I add them, it cancels. D plus 3x minus d squared d plus 3y, and that's going to equal d squared operating on 2 will give me a 0 there. Okay? Let's add these together. Now these guys will cancel out, and I want to point something out here. Well, actually, no. Let's just go ahead and do the work first, and then no, that's okay. Actually, I'll point this out. So when you're doing these problems, you'll notice that when you do the second elimination step, oftentimes you get something that looks very similar to the first elimination step. Okay, so we get something very similar to this. And look at what happened here. I had d squared times d plus 3x, d plus 3x, and I added those to get this equation down here. These guys are going to cancel out this time. When I add the y terms, those terms look exactly the same, with the only exception being that they have negatives in front of them. So I'm going to get minus the same thing, d cubed plus 4d squared plus 3d y equals 3t plus 1, okay? What that's going to do is it's going to make me do almost identical steps to what I did in the previous steps up here to solve for x. The only difference is this minus, okay? Now, because my complementary solution is going to give me these arbitrary constants here, that minus gets basically absorbed into those. But the coefficients on my particular solution here are not arbitrary. And what's going to happen is that negative is going to give me a solution that looks almost identical to this, but these will have opposite signs. Okay? So after doing that work, the dot, dot, dot means that I could redo all that work again, but it's all going to look almost the same anyway, so it's not worth doing. I'm going to get y of t equals something that looks very similar to x of t. So I have to use different labels. C4 plus C5 e to the negative t plus C6 e to the negative 3t minus 1/2 t squared plus t. Okay? So that the negative here is going to imply that I'm basically multiplying everything in my first equation by a negative, or my first solution by a negative. Whew. Okay, now comes the fun part where we have to try and get rid of these constants in here somehow. Okay, and I'm probably going to run out of space here, so I might need another page, but we'll get there when we get there. So first thing I'm going to do is take my two solutions that I got and substitute them into this first equation up here. Okay, so I need second derivative of x, first derivative of y. Now, what is my second derivative of x? What does that equal to? Well, x I found up here, and actually, here's kind of the more complete version of that. I want the second derivative of this. I have a constant that's going to go away. My c2 e to the negative t term is going to spit out a negative for my first derivative, another negative for my second derivative, and just leave me with c2 e to the negative t. This guy right here, after two derivatives, is going to give me plus 9 c2 e to the negative 3t. First derivative of this is just t, second derivative would be 1, so this becomes plus 1, and second derivative of negative t is just 0, it goes away. Okay, what about dy, the derivative of y? What does that look like? Well, dy, where's my y? Here it is. Constant will go away, this becomes negative c5 e to the negative t. Negative 3, so minus 3, c6 e to the negative 3t. First derivative of this is minus t, and then plus 1. Okay? So I found my second derivative of x, my first derivative of y. If I substitute those into this first equation up here, I should be able to set them equal to t. So I take the first thing I found, subtract the second thing I found. This minus this. That's going to give me c2 plus c5 e to the negative t plus 9c2 plus 3c6 e to the negative t plus t, and then 1 minus 1, those cancel. And that should be equal to t, according to this first equation up here. Okay? So the t's already match up. There's no unknowns in front of that t that I need to solve for. but these two coefficients should be equal to 0 since I don't have e to the negative t or e to the negative 3 terms showing up on that right-hand side. So I have c2 plus c5 equals 0. I have 9c2, sorry, that should be c3 right there. 9c3 plus 3c6 equals 0. And solving for these guys to create some substitutions that I can use later, I'm going to get c5 equals negative c2. And I'm going to get c6 equals negative 3c3. So I'll be able to use those. I have one other concern, though, and that's the constants. So if you notice, both x of t and y of t have these constants, a c4 and a c1. Because those are the same type of terms, I have this expectation that they should relate to each other in some way as well. And the reason we weren't able to find that relationship between them is because the constant terms canceled out when I did the substitution in that first example there. So what I should do is take my, my x and my y, substitute them into the second equation up here, and do essentially the same thing, but see if I can find a relationship between those two constant terms. So I'm going to do that next. Okay, what is d plus 3x equal to? Well, d plus 3x is fairly involved. So remember, I take the derivative of x. Where's my x? Right there. Okay, I take the derivative of x, which is going to look like negative c2 e to the negative t minus 3 c3 e to the negative 3t. The derivative of this guy is going to be plus t minus 1. And then I add 3 times x to that. So that's going to be 3c1 plus 3c2 e to the negative t plus 3c3 e to the negative 3t plus 3 halves t squared minus 3t. So that alone gave me a very, very big, expression. Now I need d plus 3y, because that also shows up in that differential equation up there. And what I'm going to do is I'm going to rewrite my y over here with these substitutions that we just found. Okay, so let me do that. I'm going to rewrite my y of t using those substitutions. I still don't have anything to call c4 yet. C4 is still c4. C5 is the same thing as negative c2, so this becomes minus c2 e to the negative t. And then c6 is the same thing as negative 3c3, so this becomes minus 3c3 e to the negative 3t minus 1 half t squared plus t. Okay, so now I want to do the same thing that I just did a second ago, but with my y of t function. So let's take a look at that. Derivative of y. What is the derivative of this guy? Constant goes away. This becomes positive c2 e to the negative t. Derivative of this is plus 9 c3 e to the negative 3t. Derivative of that would be negative t. Derivative of that is plus 1. And then I have to multiply y by 3. So this becomes plus 3c4 minus 3c2 e to the negative t minus 9c3 e to the negative 3t minus 3 halves t squared plus 3t. Okay, so it looks really, really awful, but almost everything will cancel out when we add them, because up here this says I add those two things and set the result equal to 2. So doing that, look what happens. These cancel. The t's cancel. The 1 and negative 1 cancel. I get cancellation here. I get cancellation here and here. And then notice, negative 3c3 e to the negative 3t and positive 3c3 e to the negative 3t. Those cancel. These cancel. Everybody cancels except for those constants, which is really convenient because that's what I wanted. So I get 3c1 plus 3c4 is equal to, what did we say, 2. Okay, so if I divide everything by 3 and then isolate the C4, I get C4 is equal to 2/3 minus C1. And that allows me to make the final substitution that I need to make for this C4 right here. So what I get for my final solution, finally done, x of t is equal to C1 plus C2 e to the negative t. I'm copying this from my previous page where I already found this, plus C3 e to the negative 3t plus 1/2 t squared minus t. And then y of t is equal to our constant, which we just found is the same thing as 2/3 minus C1 minus C2 e to the negative t minus 3 C3 e to the negative 3t minus 1/2 t squared plus t. Holy smokes. Okay, you can see that these are involved problems, and that's the reason I only did 2 of them. There are more examples we could have done. They all follow, roughly similar steps. There are also systems of 3 equations in 3 unknowns. I think I assigned 1 or 2 of those, and those will follow very similar steps as well, but they should be a good challenge. So that's going to be it for this section.